Fault port method for fault analysis. Faults are the basic hurdle for any power system network. As the complexities of the system increased, the probability of the occurrence of the fault also increased. Hence it is always better to take precautions which involve study of system under various fault conditions. This paper describes the generalized method for solving any combination of simultaneous balanced and unbalanced faults and calculating symmetrical fault port currents. This method can be applicable irrespective of any combination of faults, any number of faults and their location. Keywords: simultaneous faults, fault port voltage, fault port current. Introduction. Load flow analysis requires the calculation of voltages and currents of all buses. These values assist in the control and planning of the system. Simultaneous faults are those cases in which there are one or more faults occurring simultaneously. The reason for the occurrence of such faults may be due to lightning stroke, human-made accidents, etc., and it is quite difficult to analyze more than one fault occurring at the same time. Faults mainly occur sequentially rather than simultaneously. Keeping the aspect of protection in mind, it is desirable to compute the voltage and current during and after the occurrence of first and second fault. For accomplishing this, system has to be monitored under all kinds of faulted situations. There are different types of faults which may be categorized as balanced and unbalanced faults. These simultaneous faults may be any combination of these balanced and unbalanced faults. Balanced faults can be of both symmetrical or unsymmetrical mode. 1. An important method of simultaneous fault analysis comes from G. Gross and H. W. Hong in 1982 in the form of two-step compensation method. 2, 3. Papers 4, 5, and 6 deals with various other methods that could be adopted for simultaneous fault analysis. This paper is based on the method of multiple port theory and theory of symmetrical components given in 4. Current and voltage constraints for various fault types with reference to symmetrical components are shown in Table I7. Under the normal fault analysis condition, analyzing occurrence of fault on any phase is not a difficult problem, but in case of simultaneous faults, occurrence of faults on different phases has to be considered. Usually, mutual coupling is present between the lines, but that is not considered in this paper. The impedance matrix is to be modified whenever a fault occurs in a system. This is the mandatory requirement while doing fault analysis. This modification can be anything ranging from addition or deletion of a bus as given in 8. The sequence network interconnections are also another important point that needs consideration. 7. 2. Sequence network interconnection. The interconnection between the sequence networks must be such that all the limitations and the boundary conditions for that particular fault must be fulfilled. From Table 2 it can be seen that for some faults the currents of all sequence networks at the fault point are equal and the sum of the voltages of all sequence network is 0, from which we can conclude that the sequence networks are connected in series with each other. Similarly, for other types of faults voltages of all sequence networks are equal and the sum of all the sequence currents is equal to 0, from which we can conclude that the sequence networks are connected in parallel. In case of simultaneous faults it is not as simple as in case of single fault analysis. In very few combinations of faults these networks fulfill the connection constraints. This difficulty mainly arises due to the occurrence of faults on different phases. To overcome this problem, Z.X. Han has recommended using phase-shifting transformers to shift the voltages and currents accordingly in order to meet the boundary conditions for ideal turns ration is given as equals 1 2 equals 2 1, 1. 3. Basic network equation, where Z1 and Z2 are known as driving point impedance and Z12 and Z21 are known as transfer impedance 4. Hence, when fault occurs anywhere on the system, impedance matrix changes accordingly. This paper uses fault port matrix to calculate parameters related to simultaneous faults as given in 4. According to the multiple port theory, each fault point is considered as a port. In a port, the current coming out of one terminal should be equal to the current entering another terminal. 1. 4. Fault port matrix. In 2, although the short circuit fault was occurring, but during simulating it the impedance matrix, i.e. Z bus, was used unchanged. but usually we cannot consider it like that as the fault may occur at any point on the network. Always considering a fault point as an addition of bus may make the calculations difficult. Hence Zxhan has devised the method of fault port matrix, which is easy to understand and lesser the computation time as well. A fault port matrix elements. Taking case of a general short circuit fault at any point K on any line as shown in figure 2 and assuming the injected V flowchart 4 below given is an algorithm implementing the above given method. First and foremost, load flow is to be done to get the reference values to see the changes occurred after faults. Also, the open circuit voltage mentioned in equation 18 will be equal to the voltages obtained from the load flow. Hence, it is one of the major parts of the flowchart. The admittance matrices formed here are sparse in nature. The computation time is saved using admittance matrix in load flow analysis. Then these matrices are transformed into impedance matrices for further calculation, as the fault analysis generally uses Z-bus values for its calculations. Once the type of the fault is specified, we can proceed with the formation of fault port matrix. Fault port matrix is formed based on the method given above. Bus voltages and currents of the buses affected by occurrence of the fault are calculated. The value of currents and voltages are aligned with the boundary values. Once a particular fault analysis is completed, we can proceed with the other faults, if present. Else the algorithm stops and result is obtained. 6. Result. Data for a 4-bus system was taken from 10 and the above method was implemented on that system. Giving different kinds of faults as input, results are given below.